Sorry about that. A couple minutes late. I'll get I'll get this PowerPoint up real quick and we'll get started. Still not 17 minutes late, and there is no power outage. All right. I think we'll just get started now. So today we're going to be going a little further into free body diagrams and then start looking at graphs. So while the past 2 days were more about like actual physics content with like velocity, forces, and all that, we're going to be looking at like visual representations of physics and how to make and understand them, because this is an important skill for the course as a whole, and it's something you should probably get used to. So quick review on free body diagrams. Arrows start from a single point. Remember, the label forces and relative lengths are matter in a free body diagram. Do not remember that the extra bullet point here, but just make sure you draw all the arrows from one point. Just because a string is attached to like the edge of a block, the arrow should still come from the center. So on the AP exam itself, you'll have to draw these sometimes. You have a couple examples on the right here, where on free response questions, every now and then, they'll just provide you a dot like this and tell you to draw all the forces by drawing arrows from them. It's very hard to mess up, drawing the arrows in the correct location, but of course the lengths matter, and if you have a force that's significantly bigger than another one drawn shorter than the other arrow, you'll probably lose points for that as well. And you'll notice it says don't draw the components, draw the forces, and if you're confused by that, it basically means you'll learn how to take a force and divide it into like a horizontal and vertical component. If you draw those separately on the actual exam, you're going to lose points for that. So just draw the forces themselves. Gravity goes straight down, or in space, I guess it's a little different, but gravity goes down, normal force goes, wherever the object's from. Don't divide up the forces into smaller pieces. And even if this is the only way you're required to make free body diagrams, it can be helpful for, breaking down a situation and making it easier to understand. And just generally helping with, not confusing whether a force goes up or down. And it does also help just to figure out where the net force is going. You can sometimes just guess the general direction by drawing a good free body diagram. And also, in addition to just these dots for the free body diagrams, most free response questions do actually just give you a diagram. So like in the first one, they'll have the system of the two blocks with the string between them. In the second one, they do provide like a image of the planet with the two moons around it. And this obviously makes it helpful since you can just look at the diagram, and to get a better idea, you don't have to just use the words. On multiple choice questions, they're less likely to give you a diagram. So depending on how confident you feel about figuring out the forces in a situation, you might want to practice drawing free body diagrams just from the words of a question. But if you feel confident about that, just make sure you know how to draw a diagram for when you might see a problem like this. They don't show up on every test, but sometimes they do. And it's a good idea to know how to do these. So a few tips for drawing the forces themselves. Obviously, gravity pulls down, except for like the cases where you're in space, in which case the gravity just pulls you towards other objects. But for most cases, you're going to be on Earth, gravity pulls down, and there will be a gravity force. Tension is always pointing in the direction of the string. And even if the string is like on the top of an object but tilted sideways, the arrow should be pointing in the direction that the string is, just with an arrow drawn from the center of the object. So to put that in other words, you don't start at the center and point in the direction of the string, you basically draw in the direction that the string is slanted with the arrow positioned at the center of the object. So it's basically like parallel to the string in most cases. Normal force pushes away from where it touches the surface. Like you just take the point where you're touching the surface and point away from it. And it's not going to be like sideways relative to the surface or anything. It's always going to be straight away from the surface and where you're touching it. Friction is opposite the direction of sliding against another object. So what this does mean is if you're sliding right, but the floor is sliding right faster for whatever reason, the floor is moving right relative to you. So your friction's actually, you're sliding left relative to the floor technically, because the floor is moving faster. So since you're sliding left on the floor, then the friction force is going to point right. So stuff like this in like relative motion and points of view is something to just get used to, because it can definitely trip you up a few times when you have like one block sliding on another block sliding on a table. Situations like that, it's important to like really keep track of which direction the friction is actually going. Next up, drag or air resistance. This one's not exactly relevant because you don't really have to consider it much. It's also extremely simple. It just points opposite direction of whichever way you're moving. In a lot of situations, you won't even have to draw air resistance. I wonder if it doesn't actually say that here, but sometimes, a lot of times they'll just say ignore air resistance. It's good to know this, but it's probably not going to come into play too often. Most chromes just straight up do not care about air resistance because it's difficult to calculate. For another thing, try and go through the checklist of every single force. Like a box sitting on a table might not feel like it has any forces, but the gravity and normal force are there. They just cancel out. So you don't want to forget about those if you have to draw them. So make sure to always like go through the list of possible forces and make sure that you didn't accidentally miss anything. So this time I've decided to do some more quick checks instead of Kahoot today, because getting a whole set of free body diagrams and graphs to work with for Kahoot is a little difficult. So put these answers in chat if you guys have them. Basically just, I don't think I can get you guys to send me a picture that you guys draw, so we'll just think about the actual, like what forces are present here. So just think of all the forces that are applying on these objects. Ignore air resistance since that applies to anything that moves, which that's not helpful right now. So just if there's like a normal force, if there's gravity, think of everything. If one object's like specifically pushing another, list it like that. So, like say the force of the bat on the baseball instead of just saying normal force here. So I'll give everyone a bit to think about this, and I'll be checking the chat to see if anyone has any answers. Oh, also for the second one about getting hit by a truck, assume your feet are still on the ground. Like you're not getting sent off into space like some cartoon. I don't know what you mean by all. Just list what exact forces there are. So like in the first one, is there gravity? Is there a tension force? If so, where is it coming from? Stuff like that. If you want to, you should try to describe the direction in which they point, even if it's a little vague in this situation. Right, yeah. Keep in mind you can message directly to just host and panelists instead of everyone. And also just instead of going through each force for all of them, try to look at each situation one by one and list the forces for each situation. Yeah, I get that you mean that there's gravity in all of them, but just try to think of all the forces in each situation. Don't just think of gravity and say this applies to all of them. Think of what's applying to the baseball in this situation, and then list all the forces on the baseball. Seeing as not everyone's going necessarily in order, I'll just say that that's correct, Lena, and that's also correct, Amy. So yeah, keep going for the other situations. If anyone's confused, just in case, for the first one, think about the forces on the baseball. For the second one, think about the forces on the person. And for the third one, think about the forces on the little thing hanging at the end of the pendulum. In case someone didn't understand that already. Uh, Friction isn't necessarily counted, number one. I get that if you hit the ball really weirdly, you can have friction, but that's not something I'm trying to consider here. That's not something that was part of the intended question here. Like, assume that you are hitting the bat baseball directly straight on. Can you please try to message host and panelists? I don't want like all the answers to go to the everyone chat. But tension's not it. Like that's not like try list all the forces at once. Tension isn't the only one present. There's obviously a string, but that's not it. If you click on if you look at the message thing, there is a blue button that has everyone on it. If you click on that, you can send the messages to hosts and panelists directly instead. I'll give it a few more minutes and we'll move on to the next set of examples after I explain these. First of all, that's not the only force in the second one. Second of all, instead of just saying applied force, talk about who's applying the force and in what direction if possible. Or maybe not direction in this case necessarily, but just say what's applying the force, what type of force it is, if it's relevant, and yeah. No one has really answered the second one yet, interestingly. I'll wait a couple more minutes and I'll explain them. Did you have any actual answers for number one? Because there's definitely, it's not that there's no forces there. And gravity definitely is not the only force in number three. There is no spring force in number three. There's no spring anywhere in the situation. What just happened to, did something happen to the screen? I think Zoom does that sometimes. They probably shouldn't be doing that too much. Huh, that's odd. All right, good to know. I think I'll explain these answers now. It doesn't look like there's a lot of answers coming anymore. So the first one, the first force to obviously know is going to be the force of the baseball on the bat. That's all you really have to say for there. Just the force of the baseball on the bat, or just F baseball in like an actual, I mean F bat in the actual image. Yeah, don't just say applied force. Actually, like say what's applying the force. So in the first one, you notice F bat. And then there's also gravity in the situation. The gravity hasn't disappeared in situation one. So you'll have those two forces, the force of the bat and the gravity. Like I said, ignore air resistance. We won't count that here. There's no string or spring, so there's no tension or spring force. There's technically, the bat hitting the ball is technically a form of normal force, but in this case, you really only just say that's the bat on the ball because it's physically hitting it instead of just like sitting on a table. Yeah, there's not really any force to consider here. There's obviously no thrust force or anything. There's no rockets. For the second one, there's the force of the truck on the person. Gravity is still there. And if you're still on the floor, as in the truck's like pushing you over instead of knocking you into space, there's going to be a normal force from the floor, and there's also going to be a frictional force as you get hit. So there's four forces you have to consider here: the force of the truck, gravity, normal force, and friction. Once again, there's not going to be any sort of tension or spring anywhere. So yeah, there's four forces there. This is the type of thing you have to consider. You have to like go through every single force and like actually think, is it here in the drawing? So some of you guys missed gravity in number one because it's not exactly the most obvious force, but it's still there. You have to consider it, and if you don't draw it on a free body diagram, you're definitely going to miss something. Even on a multiple choice question, if you forget to factor in acceleration from gravity, you're definitely going to miss a few points. So you can't just forget random forces because they don't matter as much. For the third one, that's a lot simpler. You have the tension, obviously, since the pendulum is connected to a spring. I mean, not spring, string. There's no spring. It's just a string with a T. So there's going to be a tension force from that. And then, of course, gravity is pulling you down. We're ignoring air resistance, and we're not touching any sort of surface, so there's no normal force or friction here. And of course, there's no other objects to apply forces on this in this situation. So it's just those two, tension and gravity. You'll go into pendulums more in simple harmonic motion and like derive some more things, but it's important to like just understand the general idea of how the forces work on something like this. So yeah, be sure to practice your free body diagrams. Seems like people are sort of struggling with this right now. You have to consider every single force that could possibly be applying on an object. So if you have a box on a table, there's still a gravity normal force. You can't just forget some of those basic forces because that's going to lose you points on a test. Even if it's not the AP exam, you'll probably have to do something like this on a test at some point, and if you just forget, that's going to be bad. So one more quick check before we move on. it appears a couple things got cut off in the picture for no reason. But for a box that's currently sliding down a slope, like it is moving, so there is a friction force. Even if it wasn't moving, there would still be a friction force, but actually that's not exactly relevant. Anyway, which of these free body diagrams would be correct? So feel free to message answer. Just I didn't put letters, did I? Just say top left, top right, something like that. And the couple things are cut off. It's just labels of normal force. So like in the top two ones, the arrow pointing up left and the arrow pointing straight up are both normal force. The labels got cut off in the image though. Shema, I think that's how to pronounce it. And Wensi, you're both right. Amy, that's not the correct answer. That's right, Cherry. Like people are finding these sort of multiple choice ones a little easier to answer. Oh, I don't know the answers. Okay, so everyone else who's submitted an answer since I last went through the answers, you're all right. Okay, I think that's enough answers. So yeah, it is unless you want to fix your answer, Amy. Do you want me to go over it now, or do you want to just go over now, or do you want to like have some more time to think about this? Okay. Oh, people put bottom right in everyone chat. I just noticed. Yeah, that's kind of annoying. All right. Yeah, we'll just go over it then. So yeah, it's the bottom right. So obviously, all these diagrams have the same three forces: normal force, friction, and gravity. So let's consider which direction they'll be going in. So first, remember, gravity always points straight down. So that's why it's not the bottom left. In addition to a few other things that are wrong with that one. So yeah, gravity, even if it's sitting on a slope, it's still going to be pulling straight down. The reason it doesn't move straight down is because of all the other forces in the image, which, yeah, the arrows here really aren't to scale, but it's hard to get these ones to scale. Realistically, the friction force would be a lot shorter and the normal force would be bigger. But yeah. So as for the normal force, remember the normal force points away from the surface it's touching. And the reason for that is it's simply the surface is pushing against each other so that they don't like overlap. So the normal force, instead of pointing straight up, is going to point away from the slope, which means it's going to point diagonally, perpendicularly to the slope. If it's like a ball on a surface, it'll be pointing away from where it's touching the surface. In a slope like this, it's a little easier to tell that which way away from the surface actually means. And in this case, it's of course going to be a diagonal slope. And friction, if you're sliding down a slope, of course, relative to the slope, you're simply sliding down it. So the friction force will point in the other direction. So the friction force is actually going to point up here. Or like up the slope, basically. So the only one that has all three of those correctly is going to be the bottom right. Yeah, you can like, I'm not sure if there's a lot of these online, but you can always try like just think of situations on your own, like things like the pendulum. You can try to draw the forces on the pendulum at various moments in the swing, or you can try to draw the exact directions of like when two balls bounce off of each other, what the force will look like there. You'll probably get more practice of this in your actual class as well. So it's just good things to keep in mind. So moving on to graphs now, I do think everyone should be practicing free body diagrams a little more, but that's mostly going to have to like happen outside of class of your own thing because practice problems are kind of hard to make up. Anyway, yeah, you'll have a lot of these graphs. These are very common, whether you're having to plot points on the graph or it's simply just given a graph with lines like this. So the important parts of a graph, never actually don't mess up a problem just because you thought the y-axis was time. Just because you thought the y-axis was position and it turned out to be velocity. Stuff like that is going to be very bad to miss. So always double check what's actually on the axes and double check the units while you're at it. You don't want to miss a question because the x-axis said minutes and then the question asks about seconds. I don't think they do try to trick you like that much, but still just be careful. The intercepts are going to be important. Just the x-intercept and the y-intercepts, they typically have some sort of meaning, even if it's kind of obvious. And the question will always ask you to like label intercepts or sometimes just use the intercepts to find something. And then after that, the most important parts of a graph, the ones that come into the whole thought process of everything, are going to be the slope and the area under the graph. So the slope, everyone knows what the slope is by now, I'm pretty sure. It's just like, the y rise over run, stuff like that. That's going to have meaning most of the time. And also, when I say area under the graph, it doesn't mean like, okay, so So if you look at the graph in the bottom left here, it doesn't mean the entire area below the graph and like just every single box that's below the line. It's asking about like the area between the line and the x-axis. So if it goes negative, it's technically going to be like an area above the graph below the x-axis. So that total area, you're going to have to actually do this quite a bit, where you simply have to calculate the area of those boxes that are between the line and the x-axis. Sometimes they'll be positive, sometimes they'll be negative. And the sign does matter. So you're going to subtract that little trapezoid from 3 to 8 seconds. You're going to subtract that from the rest of the area because that part's going to be negative. So signs do matter. Sometimes you'll get a positive result, sometimes you'll get a negative result. That's going to be particularly important for velocity time graphs, actually. Another quantity that I'll ask you to find a lot is going to be average, like an average slope or an average value, just like an average y value, like average position or average velocity. And that's not really like an actual type of value you have to consider. It's just more of something you'll have to calculate every now and then. So we're not going to be going over what that actually means since there's no fancy meaning or anything to it. So going over some basic graph types, we're going to start with position versus time, which is definitely the easiest to understand. Remembering the definition of distance and displacement, the distance can be like all changes in the y value basically, because that's every single change position adds to the distance traveled, while the displacement is going to be simply the difference in the y value between the start and end points, because it's going to be, remember, distance between start and end point. So the position, how far apart the start and end points are, that's going to represent displacement. Don't mess those two up. The y position, y-intercept, y-intercept is always going to be like initial something as long as your x-axis is time, which is the most common situation. Every now and then you'll have something like x-axis is position, y-axis is force, but that's fairly uncommon and also like beyond the scope of what we're doing in these 4 days. But in this case, y-intercept is going to be initial position, and x-intercept is whenever the particle is at the position 0. So this doesn't mean that it's not moving. It just means it like it's touching that point in that moment. So if you have a line going through the x-axis, that's going to mean it passed over position 0 during that travel. The slope is going to be velocity, change in position over change in time and all that. And the area, this is basically going to be just like multiplying the. Okay, so slope is basically y divided by x, like the quantities. So in this case, it will be position divided by time, which is velocity. And the area under the graph is going to be considered y times x, basically. So in this case, position times time. That doesn't actually mean anything much. It will mean something for other types of graphs, though. This isn't really a complicated graph. Just like I said, don't mess with distance and displacement. Those two are something people consistently have a bit of trouble learning at first. So just making sure you don't mess it up is important. So next up is velocity versus time. This is probably a more common type of graph than the first one. Maybe just because it's a little more complicated or a little more confusing to some people. It does have a little bit of difficulty, but after getting used to it, it's not that bad. So the y-intercept, once again, it's initial velocity in this case because we're tracking velocity instead of position right now. And the x-intercepts are moments when the particle is at rest or not moving. Because remember, when velocity is 0, you're not moving. Of course, if you have like a ball that rolls up a slope and then begins to roll back down, at the very peak of its motion, it will like temporarily stop moving before. Well, it doesn't really stop moving in our eyes. But as far as velocity goes, it's going to temporarily hit 0. It's going to start at positive velocity, go down, hit 0 velocity, and then keep falling in velocity. So like a transition from rolling forwards to rolling backwards is going to have a moment of 0 velocity most of the time. And at that moment, it's considered to be not moving. So keep that in mind, even if it doesn't look like it's not moving, it can like momentarily not be moving with a velocity of 0. In this graph, the slope is going to be acceleration. And more importantly, the area under a velocity time graph is displacement. That's going to be the most important takeaway of this thing, because they love to ask about this. Your teacher probably will ask you about this more than a few times too, just because it's not as obvious as like the slope of a position time graph is velocity or the slope of velocity times acceleration. Saying that the area under a velocity time graph is is displacement. It's a little more complicated. Keep in mind it's displacement. So once you find the area, if the question asks you for position, make sure you add the displacement back to the initial position to get the final position. Because this doesn't actually give you an initial position on its own. And if they don't give you an initial position, you can never know the position at any point in this graph. You can only know how far from the starting point you are. So yeah, as well as time graphs, we're going to get a little bit of practice with this later on. So acceleration versus time, arguably the most boring, because there's not much to do here. It's the main part of this that's interesting is just looking at the area under an acceleration time graph is change in velocity, but that's basically the same concept as a velocity time graph. Just, acceleration now. The y-intercept is once again initial acceleration, and the x-intercept is any moment of 0 acceleration. Which once again, this doesn't mean no velocity or 0 position. It just means that you are temporarily not accelerating, which is mostly just relevant in terms of the fact that it means that there's 0 net force at the moment. So that doesn't mean that it just means the velocity is constant in that one moment, which again is kind of not very relevant to real world moments. I guess like if a car is speeding up and eventually stops speeding up as it reaches a highway speed, then that's going to be considered 0 acceleration. But like, yeah, this isn't that relevant. You'll probably find something asking you to use a point and plug it into F equals ma. or like use an average acceleration or something to find an average force. But these guys are pretty uncommon and there's not much to say about them either. So we're gonna move on from these. So yeah, we have polar graph off the internet because yes. So try to find the displacement from 10 seconds to 55 seconds. Remember to check the units first of all. And then after that, remember to make sure you're actually calculating the area correctly. And note that it says 10 to 55 minutes. So they will ask you just like random bounds. It's not going to be from like 0 to the end most of the time. So yeah. Those of you saying 60 should probably be reading the units a little more closely. Unless I made an error figure. I'll make sure I'm not messing up somewhere too on my end. If that was cut off, no, it isn't. It's just not labeled. It's definitely right there though. It's just the end of the blue line, basically. Uh, 3 is definitely way too small. Remember, it's not the number of squares. Keep in mind, it's the actual like displacement. So like give a unit and everything. Read the axes more closely. Keep in mind that each bar is 20 on the y-axis and 5 on the x-axis. 60 was incorrect. Remember, this is a velocity time graph. And even if it was a position time, you would have to say -60 in this case. Keep that in mind. Negative signs matter. It's final minus initial for change. But yeah, this is a velocity time graph. So remember, you have to find the area under the graph. It might be a little hard to understand at first, but I'm sure you'll have like plenty of time to go through how exactly this works in an actual physics class. It's a little hard to describe in like the few hours that we have for this course. Remember that when you're there, that doesn't mean you're at position 60. It means you're going at 60 meters per minute at that moment. So after 5 minutes passes, if you start at 10 minutes and then from 10 minutes to 15 minutes, you travel forward 300 meters since you've been traveling at 60 meters per minute for 5 minutes. So from there to there, even if the line is flat, you've traveled 300 meters. A 7.5 is wrong. All these answers are really small. Remember, the y-axis is 5 units of, it goes up by 20 at a time. Not 1, not 2, it's 20 meters at a time. Don't just count the boxes. You can count the boxes, I guess, actually, but if you do choose to count the boxes, make sure to multiply by how big each box actually is. So in this case, a box would be 5 minutes and 20 meters per minute. Like the length would be 5 minutes and the width would be 20 meters per minute. So the area of that box would be 100 meters. So each of these boxes represents 100 meters of displacement. Now you should try to find 750 is still wrong. 45 is not correct. Did you simply miscount some of the boxes, or? We'll go over this in a bit. Do I have annotating? I have annotating power, so I can draw on this graph. Yeah, 12 is way too small, and it's not 12 boxes either. I might just have to explain this in a bit. Hey. 1,250 is still too big. Remember, if the part of the graph is negative, that's going to mean that it's going to be subtracting from the total displacement since you're traveling backwards. I think I'm going to. Does anyone want more time? I think I should probably explain this one. Okay, yeah, that's correct. Right, we have one correct answer. 55 is wrong, by the way. Did I see the answer earlier? I think I'll try to explain this. I think I'll just explain this one now. All right. So looking at this, the part that's relevant, 10 minutes is here and 55 minutes is right here. So what's going to be relevant here is the area under the graph, which looks like this. We're going to be looking at this part of the graph. And we want to find how much is under here. All right. I understand simply like calculating the area using math is a little awkward for some people. So we're going to do this by counting the number of boxes. Remember, we add this part because it's above the x-axis, and because this is negative, it's going to be subtracted. Since this is positive velocity, so you're moving forward for each second you're up here. And then when you go here, you're suddenly moving backwards. So you suddenly have a negative displacement for these sections. All right, so counting the boxes here. We have 3 boxes here. So that's going to be 3 boxes. And then in this, we have 9 boxes in this square, but we're only covering half of them. So this is going to be 9/2 boxes here. Or you can simply just count this as 3 boxes and 3 halves there. Whichever way you want to count this works, as long as you do get the correct answer in the end. Down here, this is going to be 4 boxes cut in half. So this is going to be 2 boxes overall. And this is another 6 boxes here. And we only cover half of them in the actual graph. So this is going to be half of those 6 boxes. There's going to be 3 boxes here. So if we take this and we do 3 plus 9/2 minus 2 minus 3, we're going to get that this is 5/2 boxes of displacement total. The next step is to actually find how big one of these boxes is, because we're looking for the displacement, not just however many boxes. So one of these boxes here, you'll see that one box is 20 meters per minute. Using units is always helpful. We'll be going over dimensional analysis and stuff like that tomorrow. but here's a small preview of that stuff, I guess. And this is 5 minutes. Because it's half 10, every 2 lines here is 10. So if you multiply these, you get 100 meters. Because it's minutes divided by minutes cancels out. So yeah, that one of these boxes here is going to be 100 meters. So the total displacement from 10 minutes to 50 minutes is going to be 100 times 5/2 is 250 meters. Do you guys want me to re-explain any part of the problem, or do we want to move on for now? Because it looks like everyone really struggled with this. Remember, velocity time graph, displacement is area. I'm going to wave it, see if everyone understands, and then we'll move on. I think I figured out what caused that. So does anyone else have it? Does no one have any further questions? Do we want to just move on from here? I don't really see anyone saying anything. So if no one says anything, I'll just move on then. Looks like people kind of struggle. So if anyone needs to explain anything, please just let me know. Hey, doesn't look like anyone actually wants to say anything, so we'll just move on. All right, so we have another velocity time graph, and I want to try to find the distance and the displacement for this one. Remember area and how big a box is. Oh yeah, just do it from 0 to 10 seconds in this case. Notice I didn't write that. Just this entire area here. Screen split. Yeah, it's gonna be happening around that, I suppose. Right, are we working on this problem or are people having trouble with this? I'm not really seeing a lot of answers here. I'll be going over the answers at 3:55, just so that we have enough time to check all the answers. I mean, I'll check all the answers, explain the answers, and then check for any confusion. Alright. 4 is I'm not gonna actually say if that's correct. I'll just message. Oh. And it's being silly. It's not. Wait, okay, I'm just gonna. We'll go over. I'll let everyone know whether they're actually pregnant and then we'll move on. Yeah, I'll go over in a second. All right, so we're gonna go over this now. We're gonna start with displacement since it's you can like make a few little shortcuts to make that faster. So if you look at this section at the end here, you'll notice that this section is basically this section but negative. So in terms for displacement, these are going to cancel out. So we can basically just ignore this section. Once again, we can take this section and this section, cancel these out. What we're left with is we want to find the difference between this area and this area. I hate that I cannot use chat while I am using NFT. All right, continuing on. So we have 2 boxes here, obviously, and up here we have 3 boxes And then these are each half boxes. So together they're going to make one box. So this has a total of 4 boxes. So what that's going to mean is that in total we have 4 minus 2 is 2 boxes of displacement. And each box here is going to be 1 second. So this is 1 second by 2 meters. So each box is going to be 2 meters. So 2 times 2 is going to be 4 meters of displacement. As for distance, what we have to do is we can't just cancel out things like that, because every unit of distance traveled is going to be, it's going to add to distance. So we just simply add all 3 of the areas. So there's no fun little shortcuts or anything to cancel stuff. We just have to do this. So this is going to be half of 2 boxes is 1 box, another 1 box here. We have 2 boxes. 2 halves make 1 box here. And we've already calculated that this is 4 boxes. So what this leads to is a total of, if you add these all up, we have a total of 9 boxes of distance. And of course, each box is still 2 meters. So we have traveled a total of 18 meters with a final displacement of 4 meters. Make sure to get practice with this. You can probably find some practice by going online, searching velocity time graph practice or something like that. But as of now, it's 4 p.m. So it's going to be time for the next class. Thank you, everyone, and I'll see you all tomorrow.